Hello everybody and welcome to lesson 9, linear programming solution using two-phase method. The objective of this lesson is to solve the linear programming problem using two-phase method. As we know, the simplex method algorithm requires an initial basic feasible solution. Initial basic feasible solution is the slack variables put on the columns of the basic variables in the initial simplex tableau. By the way, the slack variables are added when there is a less than or equal to constraints. But if the constraints include or involve greater than or equal to and equal to, this doesn't work. This doesn't work. Thus, we solve such type of problem using two-phase method, which is a modified version of simplex method that will solve linear programming problem having greater than or equal to and equal to constraints. In this case, we introduce artificial variables. We add artificial variables to get the starting basic feasible solutions. In the greater than or equal to and equal to, we have to introduce artificial variables so as to get the starting basic feasible solutions. Let's see the steps of two-phase method. The first step is bring the constraints into equality form. So we have to standardize, we have to make the inequality to equality form. For each constraint in which the slack variables and the right-hand side have opposite signs, or in which there is no slack variables, add a new artificial variable that has the same sign as the right-hand side. By the way, you have to read it carefully for better understanding of what the step 1 tells. For each constraint in which the slack variables and the right-hand side have opposite signs, if the slack variables and the right-hand side have opposite signs, or in which no slack variables, if there is no slack variable, add new artificial variable that has the same sign as the right-hand side. Here is the first step. And phase 1, that is second, this one is the second step, minimize the sum of the artificial variables, because we are not interested in the artificial variables. We are introducing the artificial variable for the purpose of solving the linear programming only. So we want to minimize the sum of the artificial variable. We want to make them 0. Starting from basic feasible solution where the absolute value of the artificial variables for each constraint or the slack variables in case there is no artificial variable is equal to that the right hand side. So here, in short, we want to make the artificial variables to be 0. So starting from the basic feasible solution where the absolute value of the artificial variables for each constraint or of the slack variables in case there is no artificial variable is equal to that of the right hand side, that is the initial basic feasible solutions. And the third step is if some artificial variables has positive value in the optimal solution, the original problem is infeasible, because we have to have an artificial variable with 0 value for getting the solutions of the original problem. And phase 2 solves the original problem starting from basic feasible solution found in phase 1. Once if the problem is optimal at the end of phase 1. If the problem is optimal, or if the final table is optimal in phase 1, so we will proceed to phase 2. Let's do an example. Maximization z equals minus 2x1 minus x2 subject to the constraint 3x1 plus x2 equals 3, 4x1 plus 3x2 greater than or equal to 6, x1 plus 2x2 less than or equal to 4, and x1, x2 greater than or equal to 0. As you see here, there is equality and greater than or equal to in the constraint, so we cannot solve using the slack variable as initial basic feasible solution. So in this case, we have to use two-phase method. Before that, we have to standardize the problems. Max equals equals minus 2x1 minus x2 plus 0, s1 plus 0, s2 plus a1 plus a2, and subject to the constraint 3x1 plus x2 plus artificial variable, because it is equality, so we have to add artificial variable, equals 3. And second constraint for x1 plus 3x2 minus s1 plus artificial variable 2 equal to 6. Because here it is greater than or equal to, we have to subtract the slack variables and we have to add artificial variables for using as in basic initial feasible solution. And the last constraint is x1 plus 2x2 plus s2, which is a slack variable, equal to 4. And the non-negativity x1, x2, s1, s2, a1, a2 greater than or equal to 0, greater than or equal to 0. So to start phase 1, in phase 1 we want to make the artificial variable to be 0. We want to minimize the artificial variable to be 0. So our objective function will be minimization z equals a1 plus a2. a1 plus a2 subject to the constraint, the same constraint, and we have to put this into the initial basic feasible, the initial simplex tableau. So when we put here, Cj is the objective function, and our objective function is z equals a1 plus a2. So the coefficient of the other variables are 0. We put here x1, x2, x1, s2, a1, a2. Only a1 and a2 has coefficients. Thus, we put here 1 and 1, and this is the basic variables, the initial basic variables, that is a1, a2, and s2. a1, a2, and s2 having the coefficients, or having the coefficients 1, 1, 0 from the objective function here, from the objective coefficient of the basic variables. So let's put the other coefficients here: 3, 1, 3, 1, 0, 0, 1 for A, and 0 for A2. 4, as you see, 4, 3, 3 for S1 minus 1. Look, it is minus 1, and there is no S2 in the second constraint, so we put 0. And for A1 we put 0, and for A2 we put 1. And for that third constraint, 1 for x1, 2 for x2, 1, 2, and 0 for s1. There is no s1 here. For s2, 1. For a1, 0. For a2, 0. And these are the right hand side: 3, 6, 4, 3, 6, 4. Now let's find out the zj values. Okay, let's find out the zj. Zj can be obtained through this formula, that is summations of CB column times xn, and we have to add 1 times 3 plus 1 times 4 plus 0 times 1, so we get here 7. 1 times 1 plus 1 times 3, 0 times 2, we get here 4. And the same is true for the remaining. And we get like this. So this is the zj value, and cj minus zj is obtained by subtracting zj from cj, from the top row, from the top row. So we have to subtract zj, and we get the value like this. So here we have to determine, as we remember from the simplex method, from the normal simplex method, we have to determine the pivot column. Since it is a minimization problem, since it is a minimization problem, we have to determine the pivot column by selecting the maximum negative, because it is a minimization, minimizing the artificial variables, right? Don't forget that. So Cj minus Zj value, as you see here, minus 7 is the maximum value. So here is the pivot column. Here is a pivot column. This one is the pivot column. And once we determine the pivot column, the next is to determine the pivot row by taking the ratio of right-hand side with the pivot column values. Determine the pivot row by taking the least positive ratio of right-hand side with the pivot column. Hence, as you see, these are the ratio: 3 divided by 3, 1, 6 divided by 4, 1.5, 4 divided by 1, 4. So the least positive ratio is 1. So this is the pivot row. So it is the pivot row. So determine the pivot row and the pivot column. So we know that the entering variable and the leaving variable. Entering variable is x1 and the leaving variable is the artificial variable a1. So we have to replace a1 with x1. And the next task is to make the pivot value using elementary row operation to make the pivot value. The pivot value is 3 because it is the intersections of the pivot row and the pivot column. So we have to convert this 3 to 1 by using elementary row operation. So when we divide by 3, the whole row is 3, so we get 1 here. So we get like this. And the next is we have to conduct row operations to change these values, the value found on the pivot column, to be 0, to make the values except the pivot value. We have to change this into 0. We have to change this 4 into 0 and 1 into 0. So let's use this formula, that is when we subtract 4 times R1 from R2, so it becomes 0, right? So we can apply this row operation to make this value 0. For the second, since 1 and 1 are equal, so we can just apply R3 minus R1. R3 minus R1. R3 minus R1. So when we subtract R1 from R3, we get the value in the R3 column like this. Now let's move to calculating the Zj. Zj can be calculated by multiplying 0 times 1 plus 1 times 0 plus 0 times 0. So we get this. We just multiply this column with the corresponding column and add, and we get this. And once we get Zj, we can subtract from Cj, and we get Cj minus Zj. So we get this value. Once we get this value, let's look at the values in the Cj minus Zj. When we look at the values in the Cj minus Zj, all the values, some of the values are greater than or equal to 0, some less than or equal to 0, so optimality is not arrived. By the way, for the minimization, optimality is achieved when Cj minus Zj values are greater than or equal to 0. But here, there are some values. There is one value which is less than or equal to, which is less than 0, which is negative. So optimality is not attained. So we have to repeat the iteration again. And thus, we have to determine the pivot column by selecting the maximum negative from the Cj minus Zj. The maximum negative is minus 5 over 3. So this is the pivot column. This is x2 is the pivot column. Once we determine the pivot column, let's take the ratio of the right-hand side with that of the pivot column, 1 divided by 1 over 3, 3, 2 divided by 5 over 3, 1.2, 3 divided by 5 over 3, 1.8. So when we select the minimum positive, the least positive ratio, so 1.2 is the least, so this one is the pivot row. This one is a pivot row. So R2 is a pivot row. R2 is a pivot row. Once we get the pivot column and the pivot row, so we can determine the entering variable, that is x2. x2 is an entering variable and a2 is leaving variable. So we have to replace artificial variable a2 with x2. So we replace this, and the next task is using a elementary row operation. We have to make the pivot value, that is the intersections of the pivot row and the pivot column, to be 1. So 5 over 3, to make 5 over 3 1, we have to multiply by 3 over 5. We have to multiply the second row by 3 over 5. So we are conducting this row operation. We can convert 5 over 3 into 1, and the next task is to make the other value found in the pivot column to be 0 using elementary row operation. For example, to make 1 over 3 0, we can make a row operation that is R1, that means 1 over 3 minus 1 over 3 R2. 1 over 3 R2. So it becomes 0, and this, the same row operation is conducted for the other values in the row. And the other thing is to make 5 over 3 to be 0. So R3 minus 5 over 3 R2 can make this value to be 0. And the next task is to find out Zj. Zj can be calculated by 0 times 1, 0 times, since the CB column is 0, so all the values of Zj becomes 0. And now let's calculate Cj minus Zj. Cj values are here, and we subtract Zj. So we just move the Cj values because the Zj values are all 0. Now we get Cj minus Zj. The next task is to check the optimality. To check the optimality for minimization, don't forget that it is a minimization of the artificial variables. So we have to check the optimality of the minimality using Cj minus Zj greater than or equal to 0. As you see here, all the values satisfy the greater than or equal to 0. So optimality is arrived, and this is the end of phase 1. So now we can proceed to phase 2 because phase 1 is completed by optimality. And here the value of the objective function is 0. The value of the objective function here is 0. As you see here, the value of the objective function is 0, which indicates that the value of the artificial values are 0. The values of the artificial variables are 0, and the problem has a feasible solution. Thus, we can proceed to phase 2. Phase 2. In phase 2, we just take the coefficients of the original objective function. Since the values of the artificial variables are 0, thus we eliminate the columns of the artificial variables as well. We have to eliminate the columns of the artificial variables because their values are 0, since the objective function is 0. So we have to remove these two columns, and we have to form a new simplex tableau. So the new simplex tableau looks like this, and we have to take the Cj, the objectives of the original maximization problem. The original maximization problem is maximize z minus 2x1 minus x2. So here we have to replace this. And the other things remains the same. Only the CB and CJ will have to be converted or have to be changed. CJ can be taken from the maximization objective function, and these are the coefficients as you see here, the coefficients from here, and the other things remain the same. That means these are the results that is obtained in phase 2. Now let's calculate Zj. When we calculate Zj, we just multiply minus 2 by 1 plus minus 1 times 0, 0 times 0. So we get here minus 2, and we get z equals minus 12 over 5. Now let's calculate Cj minus Zj, and we get the values. So our problem now is maximization. Don't forget that, because this is our original problem, right? So it is maximization. So our optimality should be checked with Cj minus Zj less than or equal to 0. So as you see, all the values of Cj minus Zj raw values satisfy Cj minus Zj less than or equal to 0. Thus optimality is arrived or achieved. Thus Z max equals minus 12 over 5, and x1 3 over 5, x2 6 over 5. This is the end of phase 2. By the way, you can solve this linear programming using big M method, and we will solve this same problem using big M method in the next lesson. This is all what I have for today. I have provided you an exercise, so try to do it, and if you encounter a problem, you can write it on a comment box. Thank you for listening. We will meet with another lesson. Till then, have a good time. Bye.